here we go. We have a algorithm, Hierholzer algorithm. So before that, that's a prerequisite. I hope you are already familiar with the Illyrian path and topological sort. So before jumping into the algorithm, let us solve the problem first. We have this problem, valid arrangement of pairs. So you have given a zero index array, 2D array pairs, where pair I is equal to starting index and ending index. A arrangement, an arrangement of pairs is valid if we have previous index, so previous pair ending index should be equal to current pair starting index. If there are multiple answer, we need to return any of them. So we have this test case. In this 11 9, so the next pair starts from 9, so 9, so it will link to this. Then we have 4, it will end on 4, 4 will link to this 4, then it will reach till 5, 5 will link to this 5. So this is a valid arrangement. And in this 1 2 3 3 2 2 2 2 1, so we have two different options also, so you can return any arrangement. Then we have this 1 to 2 2 to 1, then 1 to 3, so we have to return a 2D array. So it is also given the arrangement is valid, so we need to return 2D array, and we have also given 2D array. So let's try to build this. So I have taken this test case. In this test case, we have 11 to 9, then we have 9 to 4, then we have 9 to 3, then we have 4 to 2, then 2 to 9, this, then from 3 to 4, then from 4 to 5, then 5 to 1. So in the Illyrian path, what we have? We have to visit a particular edge only once, only once. So in this case, we also have that particular case. So if we start from this index, then if we start from, actually we have 5 to 1. So if we start from this particular value, then we reach this, then we reach this, then we reach this, then we again come to this, then we go to this, then 4, then 5, then 1. So we have followed one edge only once. So that's how we have to visit a particular pair, and we have to return any path. So let's find out what we have. We first have to build a graph. So as you can see, this node goes to this node. So we have a node. So this is incoming edge. This is outgoing edge. So this is my out, and this is my in. So as you can see, can we start from here? Can we start from here? No, we cannot start from here, because after that we can reach to this, then we can reach to this, then this, then we again come to this, this, and this. So but this is missing, so we cannot start from this. Why not we cannot start from this? Let's analyze. In Illyrian path, what we have? In the Illyrian path we have so let me change the color. Incoming edges, incoming edges. So incoming is with green. So we have two incoming here, we have zero incoming here, here we have two incoming, we have one incoming, and here we have one incoming, and one incoming. But we have 9 4 3, so 9 4 3, then we have 2, then we have 9, yes, then we have 4, so 4, then we have 5, then we have 1. So this is valid. So let's find out the outgoing edges. So outgoing, and here we have incoming. How many outgoing we have? Here we have one outgoing, here we have two outgoing, and here we have two outgoing, here we have one outgoing, here we have one outgoing, and we have zero outgoing. So its outgoing is more, only its outgoing is more, so we can only start from this particular node. and no other node, because its incoming is more than outgoing, so we have to start from this particular value. So let's take one another example. What if we have this 11 to 9, 9 to 9 to 4, then this. So we have 11 to 9, 9 to 4, and 4 to 11. So let's first find out incoming edges. So 1 1 1, and outgoing is also 1 1 1. So we can start from any node, because we have not find any incoming. So we will just pick this. Starting will be pairs of 0 and 0. So we'll start from this node, so we can visit any node. Initially we set our starting to this node, because this is a cycle, and the incoming node is not more than outgoing. So we have found out from where we have to start. So now let's first find out our incoming and outgoing. So incoming, we have a map of integer and integer. Then for outgoing we also have a map of integer and integer. Then we find out if the incoming is more than outgoing for any particular node, so we can just traverse in our map key set and we will check. But there's a chance that this particular index, that this 11 is not in the outgoing, 11 is not in the incoming. So you can do um, by any mean. So we will show you I will show you the code, but let's first focus on the intuition part. So we have find out from where we have to start, but uh, this is our starting point, but we have to find out the different ways. So from 11 we can go to 9. From 9 we have two different paths, either 3 or 4. Then from 3 we have only one path, 4. So as you can see, this is my map, and here we have list of integers. So I will say graph. So I will say this a graph. So I will store this 11. From 11, if we find any particular node, we will just add it here. So we have, let's say, this 9, this 9. So if in the graph we don't have 9 starting point, so first we will add a 9 as a starting point, then we will add its corresponding ending, first 4 then 3. So we will add this. Then this is our Illyrian path. Till now we have covered our Illyrian path. So we will start from this. We know our starting position. Then if we start from this, and in this case any path is valid. So we can either go to from this, then we can go to this, then we can go to this, then this. But this path is not valid. This path is not valid. Uh, we don't have to find each and every path, and after that we have to check. No, we can optimize it. So for DFS, it will be V cross E time complexity, but we can optimize it. We don't have to find any path. We don't have to find each and every path. So what we'll do is, we know the path is look like this: 11, 11, then 9, then it will reach to this. So 11, 9, 4, then it will go to 2, then 9, then 3, then 4, then 5, then 1. Then 1. So this is my path. This is my um, this is my pairs. So 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7 8. So this is my 8 different pairs, or we can say path. So I will store this in my list. So we have two different paths. So now topological. sorting comes in picture. So first we have this, then what we have in topological sort. From U to V, every U comes before V. So every V comes after U. Every V comes after U. So using topological sort, I hope you have already solved topological sort using DFS. And I hope you already know why we add the node after the topological sort. So after the DFS function, on our last line we add current node. So I hope you are already familiar with this concept. So then we will follow that particular concept here. So we have this, then we go to 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 this. So we can go in any direction. So then we will add this. We cannot go it further. Can we go it further? No, we cannot go it further. So just add it here. Then we have this. So can we go it further apart from 5? Yes, we can go it. So then we have this. We can go, yeah. So we can go to this particular node. So after that we have traversed this. We have only one way left. So we will go to this node. So then we will come to this, but we have traversed this. We have traversed this. How do we detect if we have traversed that particular edge? That if we have traversed that particular edge initially, for starting from 4 we have two different paths, 2 and 5. If we go to this node, we will just pop out. So then we reach this, then we go to this, so this, then we will just pop out. We will just pop out this node. So then we reach 9, then we reach 3, then we reach 4. From 4 our list is now empty, so we cannot reach it further. So we will just add 4. So let me add commas. Then we will backtrack. We have 3, so we will add 3. Then we have 9, we will add 9. Then we again backtrack. So then we have 2. So for 4, then we again have 4. We have traversed this our map value correspond to key value 4. So we have this list as empty. Then just add 4, then 9, then 11. So this is a valid path. 4 9 11 9 4 2 9 3 4 5 1. So this is a valid path. So let's code this. So we have map, and in map we have three different types of map. First is graph, in degree, out degree. Then we have a path to find the path. Then from graph, if this particular starting position we don't have corresponding list, so first we'll add the list, then add the ending point. Then in our in order map, um, in degree map, yes. So we are first adding our starting position. If starting position is not there, it will just increment, it will just take 0 and add +1 frequency corresponding to that. If the frequency is already there, it will just add +1 frequency. So same applies for out. So in and out we have. Then we need to find the starting position. Initially I am taking starting as pair 0 0, but this is for loop. If we don't have a loop, we have to check for key out key set. This is my out, so I am traversing in the out. So what we have, out degree dot get, we are getting, but for the corresponding out there may be a case that for this key it is not present in our in map. So we have to find by using get or default. So if this present, it will pick up the key, the value corresponding to key, as it will pick up 0. Then we are adding. So in degree should be less than out degree. In degree should be less than out degree, and the difference should be 1, not more than that. So if the starting node, there's a 1 less incoming, there's a 1 less incoming, In case of cycle, I can take any starting position. So why not I can write out degree greater than in degree, because let me tell you, let's take this case: 1, then 4, so then 9, 10, then 2. So here the in degree, is 0, out degree is 1, in degree is 1, out degree is 3. So out degree is more, but starting position is this. So that's why the difference should be 1. So we have this, just break out after finding starting position. After that, think like topological sort. We start from the starting node and want to visit all the nodes but only once, like Illyrian path. So we will first visit the neighbor nodes, then we will add the current node. So there's a direction from U to V. All the U comes before V. So I am passing starting, my graph, and a path. Path is a list. I will add a node in my list. So this is a DFS function. First, we have neighbor. So we will getting the corresponding list in the map. So we have neighbors. So we first need to traverse the neighbor. If neighbor value is not null, there may be a chance that we are at the ending node. So after that we don't have any further neighbors. So neighbor is null. If we don't have null value and size is greater than 0, then only visit the neighbor node. So neighbor node, this is our neighbor value. We are removing from the list so that we will not visit that particular edge again. Neighbor has same object reference as map value, as it is present in the map. So changing in list, this particular list, neighbor list, will also affect map key value. So that's why we can directly remove it from here and it will affect our map. Then just traverse the neighbor node. After traversing all the neighbor nodes, we are at the ending node. So add that node on the 0th index. Then we are at the head node. So add that node on the 0th index. So all the paths is in the valid order. Then we just need to build our answer. So answer, this is my answer. Where is the answer? So answer, we have answer here. So we are building our answer. So from path I to path I plus 1, we have a path. Then just return the answer and this code will just work fine. But in this video, we will learning Hierholzer algorithm. So what is this? It is just optimization, or as we have done in the DFS code, it will do this in an iterative manner. No, nothing more than that. So what is a DFS? DF is a recursive stack. So Hierholzer is just using the iterative stack. So let's find out. So we have this DFS function, just remove the DFS function and that function. Then we have a stack. So first we are adding the stack as we are calling our recursive function using the start value. Then peak, just look at the starting node, and if the corresponding neighbors is present in the graph, then go to that particular node value, and we were just removing that node from our graph. Push that, because we are calling our recursive function, so that's why we have to call using the neighbor node value. So if we are at the ending node, so just pop out from the stack. We are just removing that node from the stack and add on the 0th index the popped value. So that's about the this algorithm. Let's submit this and let's talk about time and space complexity. In this code, what we are doing, we are visiting a node and a edge only once. So its time complexity is v plus e, and the time complexity is v plus e, and the space complexity, we have this map, this graph, space complexity is also v plus e. So I hope you all learned something new. Thank you all for watching.